Thank you, Floppin. Thank you so much. I forgot to turn on the mic. Oh yeah. So yeah, good evening and welcome to another evening of PICO-8 coding. And this time I'm gonna be showing you how to use tline. Thank you very much. Professional streamer, not. But yeah. So anyway, tline is a function with which you can draw textured lines from the sprite map, and this came in PICO-8 0.2.0, which came out I think 2 weeks ago, and it's basically a huge deal. It allows you to do all kinds of effects much cheaper than before, and here you can see from the PICO-8 manual. This is straight from the PICO-8 manual what it does, but instead of letting the manual do the talking, let's have the effect itself do the talking. So let's start doing something with it. So first of all, let's go to this sprite editor and let's get us some tiles, and let's just make really simple one color tiles. And now let's go to the map and make a texture with it. So oops, not the whole map, like this. Now we have a yellow and like orange and red grid, and so let's just copy this here and this for nodes. So we'll have to consult them again, and now let's make a basic loop here. So again, frame counter equals 0. Update frame counter every frame and draw. And let's clear the screen. And now, just a second. So let's do a loop let's do a for loop for y is 0 to 127. Do. And now let's start using our tline. So just like this. The first four arguments are line coordinates like normally. So let's do like 0, y, 121, y. The next, the mx and my are map tiles. So, and they're like map tile coordinates. So like this, and the following. The next final two arguments are the delta values. So basically, it starts drawing the line from the first two coordinates and starts drawing it towards the next two coordinates. Starts drawing it from the map, from the coordinates we have given it, and then every pixel it advances on the map according to the delta value. And these are map tile coordinates, not pixel coordinates. So if we want to advance 1 pixel, it's going to have to be 1/8 of a tile. So now if I did this correctly, it should draw from the map. Let's see if that's correct. And of course I forgot to save the actual actual patterns, no worries. Let's, okay, now it should be drawing them. Yeah. And we can also cycle them, because we can use these spokes here to set it so that it only loops a certain area of the screen. It has to be a power of 2. So if we wanted to loop the 2 by 2 area, we can do it like this. And oh yeah, because it needs to be lowercase, unlike in the manual. And let's see now. Okay, now we have a grid there, and this isn't all that impressive yet. Like, okay, now I'll show another feature that came in the new version of PICO-8, a built-in performance monitor. And as you can see, this is basically now on 60 frames per second. This is taking half the CPU. So, and that's not really ideal. This is, I'm going to show you, I've seen people use this for, like, some people have done like raycasters with it, like Wolfenstein type raycasters with it, and the problem with that is that SSPR is still a lot faster if you're drawing vertical or horizontal lines from the sprite sheet. Let me illustrate. So instead of this, let's do it like this. So SSPR, what was the SSPR syntax again? Sorry, I'm gonna have to remind myself how SSPR works. So what order were the? Oh yeah. This is the order. So if we do it like this. Okay, did I do that correctly? Yeah. Oh, damn it. Sorry, I forgot that. This is probably gonna happen a couple of times. I forget to save things that I've made in the sprite editor. But anyway, so now you can see if we do these vertical lines with just the SSPR, it's a lot faster than with T-line. However, now I'm going to show you what you cannot do with SSPR. So now let's do like this. Okay, so let's define our texture coordinates. So these are going to be the texture coordinates for the left-hand corner. So U is going to be -8, and V is going to be -8 plus Y divided by 8. And now we're going to have to define our delta values. So U delta is going to be again like this, and V delta is going to be 0. So what we can do now is rotate these things. So let's define that theta equals something relatively slow to begin with, and no, we don't want Facebook integration on our PICO-8 demo. So, and now let's calculate the trigonometric functions for this. We don't want to do that in the actual while loop. And cosine theta equals cosine theta. Now, let's rotate these values. and then the same for the delta values. And now let's put these in our tline function. And let's see if that works. And now, lo and behold, it rotates. Isn't that wonderful? It could rotate faster. Let's start like this. A little bit more, a little faster. We need speed. Alright, great. And then let's do one more thing. Zoom equals 1 plus 0.9 times sine of f times 0.003. And now let's multiply all these values with our zoom value. And does it work? And whoa! Look, wouldn't you look at that? We have a rotozoomer. Isn't that wonderful? Let's look at it for a while. Yay. Yeah, now we have a rotozoomer. So let's make a function out of that and save it for later. Now, let's do something else entirely. So, we're going to start by again, determining a zoom value. This time let's have it be something like 100. And then we're going to define a trapezoid. So, and our trapezoid is going to be called UV. So, E1 is going to be how did I do this? Minus zoom times 8. Oh, okay, so yeah. Do this minus zoom, actually, minus 8 times zoom. B is going to be zoom. And UV2 is going to be the other side. Okay, so this is going to be our horizon. You're going to know what I mean in just a while. And now let's do two more vertices. So, like this. So, now we're going to define the reciprocals of all of these. Actually, let's do it like this. This is going to be faster. For I equals 1/4 do add UV rec u equals 1 divided by uv1 u, and v equals 1 divided, no actually, uv4, oh yeah, that's a typo, thank you very much. And that's also a typo, thank you very much, Neurosis. Yeah, that's just basically me messing everything up like usual. And now we have the reciprocals for all of the UV coordinates. And now we need two slopes. One for the left hand side, one for the right hand side. So our first slope is going to be U equals UV3 U minus UV1 U, and we're going to divide it by our zoom value. Then we're going to do the slope for the, no way actually. We actually need two slope. No, yeah, we need slopes for both of, yeah, sorry, I'm just, so is that right? So that should be the slope for the left hand side, and now the slope for the right hand side. And I'm going to be explaining in a while what I'm doing. So now let's do our loop. So now we are doing draw lines. We can now use these reciprocals to figure out the UV coordinates of the left and the right side of the scan line. So U1 is going to be 1 divided by, oh yeah, so urec is going to be uvrec 1 u plus uv slope 1 u times, actually it didn't have it, times, I don't know, times y of course. So that's the reciprocal of one of the u's, and now from this reciprocal we can figure out what is the actual u. It's going to be 1 divided by u rep 1, and can do the same for the other u value. No, it actually has to be like that, okay. And now we can also interpolate our v's using this same method. So now we should have UV values for the left side and the right side of the scan line. And now we can use these to determine the deltas. So delta is U2 minus U1 divided by the amount of pixels, so that's 128, and V delta is like that, also like that. So if I did everything correctly, let's see if I did, I probably didn't. Oh yeah, and we could actually send the camera lower. So let's see if I did this correctly. So T-line 0 and Y and 127Y. Our starting U and V should be U1 and V1, and our delta should be U delta V delta. And let's see. Oh yeah, this doesn't need to be in the loop. Okay, did I do this correctly? I did not. Direct 2. There is no. Oh yeah, missing it. This should be V. And let's see now. Is it actually? Okay, now what am I doing wrong? Okay, let's see if it's actually drawing lines. Okay, so that's not the issue. So what is the issue? Oh yeah, I'm not defining the loop. So did that help? No, it didn't. I hope I'm not gonna have to consult the code I wrote earlier today. Oh, it's not drawing anything because it's not calling any one function. Okay, so now I've messed that thing up. This is unfortunately not something that's new to me. Okay. What if... Okay, so what's the problem here? Now I kind of think I've got an inkling. Or do I? Okay, I'm gonna bite a bullet and consult the code that I wrote earlier today. Okay, I was just... What does that do? Okay, that looks still not good, but better. And let's copy this. Okay, it's better. It's still not what we want it to be. Is it checkerboard not plain? Yeah, that's one issue, but you're using UV rectangle U for VREC2. Let's see. U for. Wait a second, UV rec. Oh, yeah, here. Thanks very much. Thanks very much, Alpha. So, does it work now? There's still some issue here. And the issue is probably this. Okay, now yeah, there's still something wrong, and this is again a case of it worked fine earlier today. Good thing I actually wrote the code earlier today, so... But, oh yeah, now we definitely need to... Okay, yes, now it works. Excellent. And... we can also... now... you move our camera around, so let's add 0.1 to the F value, the V values every frame. And now it moves. And this still isn't something that we couldn't do with SSBR, so it's rotating time. So now we're going to rotate our trapezoid. And of course we're going to need to actually define the theta. I'm just saying this bit here because if I don't say it, I'm gonna forget it anyway. And let's copy this. And hey presto, it moves. It's a bit fast. Now it rotates like that, and now you can see that because the resolution is a bit limited, there's not much to do anti-aliasing with, so near the horizon it looks a bit ugly, but we can do this about that. So if the modulo of y 2 equals 1 and y is smaller than some value, let's say 20, then now let's see, we're gonna shift our palette. So 9 is going to be 2 and 8 is going to be 1 and 2, which we're not using yet, is going to be 0. And if we're not doing that, we're gonna have to remember to reset the palette. So let's see what it looks like now. Alright, then. Okay. And the 20 is a bit too much. Let's try 10. Let's try 8. And now we're using a cheap trick to shade away the kind of ugly looking horizon. So now let's call this function pseudo mode 7 in reference to the Super Nintendo graphics mode 7. This isn't exactly the same thing, but it does a similar thing. So, and let's add that to our drawing. And of course, wonder how the original mode 7 of Super Nintendo solved the aliasing on the horizon. Actually, I don't know. I should analyze that, but I would guess that it's just basically, I don't know if there's some sub-pixel tricks. I don't know if they just avoid drawing that far into the horizon, or just use textures that look good even with the aliasing. But yeah. But anyway, of course our map doesn't have to be just a grid. So let's draw a larger map and do it in our init. So for x is 0 to 31, or y for 0 to 31, and I think it was mset. So yeah, mset x, y to be the ceiling of random 3. So now it's a value of 1, 2, or 3. And of course, now that our grid is going to be 32 by 32, we have to change these folks here. So now, every time we start this, we have it generates an all new map. And now, let's get our rotozoomer back. Chart before the pseudo mode 7, and do I have a CLS somewhere where I shouldn't be having a CLS? Oh, I'm not resetting the camera after the mode 7 draw. So now we have that thing there, and we don't need to draw the whole screen anymore, so let's go from 0 to 64 instead. And now, let's make another pattern. So, okay, we don't need these anymore. We're here just to illustrate the SSPR thing. So let's get rid of these. And now, let's make a new texture. Let's make it 2 by 2 grid. And we're just gonna need two tiles for it. So let's make something that looks like this. And then make a mirror pair for it. I'm not sure if you could just copy this and then mirror it. If there is such a functionality, then I'm not aware of it. So, and this. And now let's draw it on our map. Oops. So let's bring it like somewhere in. So this should be, where's 32? 32 is here. So oops, I'm still filling. I'm not supposed to be filling. So 32. And now we can use the other thing. This just came in 0.2.0 D, the newest version, and we can use this as an offset. I'll show you what I mean. So, okay, now we're gonna have to remember that it can't be uppercase. So, and our offset 0 is going to be, offset X is going to be 0, and offset Y is going to be 32. And it didn't work because I forgot to save save what I actually did. Now, and oh yeah, and we need to remember to get rid of the offset in our function here, so we can have our both there. Okay. And let's do a similar shading thing here. So if no, not here. Here. So if modulo of y equals, modulo y of 2 equals 0 and y is greater than, again, let's say 10. So which colors did we use? We used 2 and 1. So let's make it so that 2 is 1 and 1 is 0. Let's see how that looks. Double equal, of course. Oh yeah, actually 54 because we want it to be that way. And then it's still missing. And let's make it a bit lower. And now let's change this to 1. Okay, that looks like that. And now we have a rotozoomer sky, but let's do something a bit more psychedelic with it. So we can. There's nothing stopping us from modulating the V values on every scan line. So let's modulate it by f times 0. Let's modulate the V by 0 times f, just like that, plus y times, well, let's try to make it like that. Let's see what that looks like. Okay, it's a bit hectic. And it's maybe a bit fast. And it's still a bit fast. And we might actually not want it to modulate it that much. Okay, Now it looks like that. And let's also do something with the U value. Let's do something like that. There. Now we have a sky that does that. Let's zoom a bit more. No, actually we want to zoom less. I mean have a smaller zoom value. There. Now we have a sky that looks like that. If the person who made the Earthbound games, the mother games, wanted to do a new mother game on the PICO-8, then please contact me. I would gladly do visuals for that game. So, let's look at that for a while. Now, let's move on. And now we're gonna enter territory where I'm gonna definitely have to look at the emergency notes, I'm afraid. So, I prepared this just because I knew I won't want to write all this 3D code again. I've written it in a previous episode, but if in case all of this is new for you, I'll just go through this quickly. So this is the draw cube function. This defines our cube. This here rotates the vertices of our cube. This calls the function that projects the point into screen coordinates. This calls a triangle filling function. That PICO-8 doesn't have a triangle filling function built in, so you have to make your own. And also, for now, after we're trying to fill the triangles, we're also going to do a wireframe for it. And this bit of code here checks if the vertices are in clockwise order after projecting. So if they're in anti-clockwise, then the face is pointing away from the camera and will not be drawn. And with some other model, we would also want to somehow arrange our faces so that they're drawn in the correct order, but we're not. This cube model has no visibility problems that aren't solved with just calling the back faces. So let's see if I pasted that correctly. And I did. We have a cube. So you might have noticed that our vertices have 5 coordinates this time. And you probably guessed correctly, these are UV coordinates. So let's make a texture for our cube. So I'm going to put it here. So let's make it a 2x2 grid. Something like this, fill it and make the edges a bit smoother. Like this, smoother still, and no. Here as well. Oops. And while we're at it, let's draw something in here. So let's do it like this. And let's draw some nice shading here. One more shade. So, like that. And now we're drawing that into our map. That, and then let's draw a black border around it just in case there's some overflow. Now let's save it, now that I remember to save it. So now what are we going to do with our functions? Well, obviously we're going to have them do something with the u and v values. So let's start here. So, 2 and 3, 2 and 3, and these they have to be 2 and 3. This have to be 2 and 3. Now let's go to our flattened point function. It has to be receiving the u and the v, and for now it just passes them right back. So now let's send these to our triangle fill function. Now our tri-fill is here, so and we're not actually needing these here yet, but let's have it receive them anyway. So now we actually need to send the u and v values along with the z receive x and y values. Oh yeah, and the x4 is because we need to. The way we're doing this is we're splitting this into two flat-based triangles. So we're basically we're sorting the vertices by y, and then we're drawing a straight line to the middle vertex and splitting the triangle there. So we're making a fourth vertex. We're going to be calling it 4. So we don't need y value for it because it's the same as y2, but we do need the u and v values for it. So and these are basically the last value is just the direction in which we're drawing. So the top triangle is the y is going to be incremented by 1, and in the bottom triangle the y is going to be incremented by -1. And I've written it like this because -1 is 2 tokens, 0x FFFF is 1 token, and it's the same value. So now let's go to our flat trifill function. So now it receives all this information. So now it does a slope because it needs to increment the x values of the line it's drawing every time. So here's how we calculate the slope for that, and now we need to use that to interpolate u and v as well. So yeah, it just basically makes 2 copies of the top or bottom vertex and moves them around the 2 copies every time it draws a line. So now it's interpolating the u and v values. So now we can determine the delta for u and v. So u delta, and this is where I'm probably gonna mess up. So u delta is uv minus ua, and we need the length of the line. So the length of the line is going to be the absolute value of xb minus xa. And yes, this obviously is going to lead to the problem that at one point it's going to divide by 0. Fortunately, PICO-8 will not crash when it divides by 0. It just results in something like 32,768 or whatever the maximum number for the 16-bit fixed point values was. That's sometimes a bad thing, and sometimes we need to work around it, but now we don't have to worry about that because it doesn't have much of an impact here. So now we should have the correct UV values. So let's see if I'm doing this correctly. So UMVA, U delta, V delta, and obviously we need to remember to actually increment the U and V every time. Okay. Now, let's see, did I remember everything? I guess I didn't. Oh yeah, we need to make sure that x2 is on the left side. So if x2 is greater than x4, then we change the vertex 2 and vertex 4. So this means that it's always going to draw from left to right, and was that enough? No, I'm still doing something wrong with the interpolation, and I hope it's this. Using the wrong slope to increment U. And we're getting there, but there's still something I'm doing wrong. Am I doing this in the right order? So, is that it? I'm not sure if that's better or worse, but it's different. So these are, I think, correct. They should be correct. Okay, I'm gonna figure this out for a while, and if I can't figure it out, then I'm just gonna check the code I wrote earlier today. Right, someone says anything obvious here, because I don't see. Oh! Wait a second. Am I still Okay, now I know at least one thing I'm doing wrong, because I still have this in the draw state, so it can't even reach that area in the sprite memory. So we need to be using the 64 by 64 area from the sprite map. And yes, now it doesn't work, but now it's at least showing as a texture. So there's still something wonky here. I remember that I had to do that, but what effect I... Strange. Am I doing this at some other point? Because I remember that I had to do that earlier today, but now it works. Okay, we have a cube, and now let's give our flat trifill function a more appropriate name, flat trifill affine. Because this kind of texture mapping where we map everything just linearly is called affine texture mapping, like what you saw on like PlayStation 1. And the problem with affine texture mapping is that it has some really noticeable perspective distortions. So let's bring the object closer and it's gonna be more visible. So yeah, it wobbles around like that. And there are some ways to fix that. The easiest and the computationally cheapest way to fix that is just to reduce the amount of perspective. So let's, after all the rotations, let's multiply every z value by, say, 0.5 and make the camera a bit further away. Oh, yeah, that. And let's bring it closer. So now, as we see, there's less depth in the space. There's less perspective. So that means there's also less perspective distortion. There's also another way. I'm not sure if I have time to do that, because I'm going to try to be ending in 25 minutes. But the other way to do that would be to actually use perspective correction. So I have a note about it in here. So for this, we need to get the reciprocals of z and u and v. So let's have a new function called flat trifill correct. And let's start by defining the reciprocals. So these values, so the reciprocal of z, u divided by z, and v divided by z, we can linearly interpolate those. So let's define those. So zr is 1 divided by z, ur is, oh yeah, we need to do that for every point. So z1, oh yeah, we actually need to fill our triangle filler the z value, so
you had a dream.
So let's add this to the affine texture map mapper function as well, because it needs to receive them even if it doesn't do anything with them. Did we do that correctly? Yes. No errors there. So now the reciprocal of z1 is 1 divided by z1, and we'll do the same for u and v. So and now let's do that to v. Oh yeah, let's name this correct. And now let's do the same to v. And now instead of interpolating the u values and v values directly, we're going to be interpolating their reciprocals. So might actually run out of time, but I'll do as much of this as I can. So z. So like that, and let's do the same thing to u. And v. And now at the start of every scan line, we can get the corrected values back. So let's start with z. So ZA is 1 divided by the reciprocal of and ZB equals 1 divided by the other reciprocal. Now we can use that to determine u and z. So UA is the reciprocal times ZA and we can do the same thing with V. So now we have corrected U and V values for every scan line. Now let's call flat trifill correct and see if Z3 a nil value. I don't have a Z form of this. That's the issue. Okay, was that it? CBR is still a nil value. Because of a typo. Slope UA is a nil value. Yeah, because we're no longer sloping the values directly, and now we need to slope Z as well. In the reciprocal of Z. So, and I've written VRA somewhere here. Okay, now it has texture, not just perspective correction for every scan line, but as you can see, it's not exactly cheap. So, with the affine texture mapping, it still occasionally goes above 100% CPU. With perspective correction, it's there almost all the time. So, and it's gonna get even more expensive when we actually subdivide these scan lines. Do I have time for that? I'm gonna see. This is gonna take some time still. So, let's define a length for our groups that we're going to subdivide the scan lines in. So let's start with 16. Actually, you know what? I'm sorry. I'm not gonna show how to do this because I don't have enough time. I'm just gonna do some experimentation with what we have here. But yeah, so let's get back to our affine texture mapping because it looks pretty fine with the object we have, and of course we can still reduce the perspective, make it look like that. So as you can see, it definitely reduces the distortion. So let's bring the object a bit closer still. Let's see if we can do something to optimize this, because it's okay. So now obviously we no longer need the Z values for anything. Let's see if this crashes if we just don't calculate them. Doesn't look like it causes any problems. I do wonder, because I did pretty much a similar program earlier today and it ran faster than the program here, so see if we can make this run smoother. Something we can do here. I don't actually think there's... Okay, we don't actually need these, and it doesn't seem to be crashing. I want this to run at 60 frames per second because I know it can run. at 60 frames per second. So am I doing something I don't absolutely need to do? Is there something in the other function? Let's see, which one of our functions is taking the most out of the CPU? Our rotozoomer is taking quite a lot actually. We can probably do something about that. The mode 7 is also gulping up a lot of CPU power, and the cube drawing thing that much. So let's see if we can optimize the For example, is there something we're doing every frame or every scan line that we don't need to be doing? Okay, these are multiplied by y, so I cannot do much here. What about a rotozoomer? Well, this is something that could be done outside the loop. It probably won't save much, but let's see what happens. Because that's... No, we cannot, because we need to rotate them every scan line. Actually, for now I'm just gonna send the object a bit further away from the camera, and now it runs fine. So, do I still have time for one little thing? Let's do this trick. So let's only draw every second line of this sky. So now it looks like that. Okay, we already have a lot more CPU to work with. We don't need that modulo thing anymore. And so our sprite map is relatively empty, so let's do this. Get back to our draw loop. Now let's empty the screen using some color we haven't used, like 11, and then draw the cube on top of that. How does that look? Okay. Now let's copy this to our sprite sheet. So mem copy, and let's put it in. So this memory area is in a sprite sheet. This memory area is on the screen, and we're gonna want to copy this amount of stuff too. And let's see if we did that correctly. So after this, we're going to draw our whole sprite sheet on the screen, and it seems that we did do that correctly. So now let's clear the screen. We don't have to draw the cube again. So let's set 11 to be transparent and draw the cube from the sprite memory. So am I doing this correctly? And the 0 needs to not be transparent. Okay, and wait a second. Am I now messing with the palette somehow, because now the rotozoomer looks like that. Let's get back to here. And comment these things out for a while. Oh yeah, and CLS needs to be commented out as well. So wait a minute. I think I'm overwriting the map. Let's see if that's correct. If that's true, then we need to draw the sky texture here instead. Now let's save that. Let's put an offset into our rotozoomer. So that's 36 and 0. So was that it? Because the map and the sprite sheet, they share some amount of memory. So I might have just overwritten the map area where the sky texture is. Oh yeah, that was the issue. So what can we do now? Well, we can do this. So what colors did we use for the cube? We used 9, 4, 2, and 1. So let's set all of those to be 0. And now let's redraw this sprite. So from the same area, but let's draw it a bit lower, squeeze it a bit. So now it maps it into the half height area, and now the last two values are booleans for flip. So we don't want to flip it in X direction, we do want to flip it in true direction. And reset the palette after we're done with that, and let's see what that looks like. And we have a shadow, but we're probably gonna want to draw it before the cube. Well, what happened? Oh yeah, obviously I don't want to reset the palette there, so I just want to reset these values. not the entire palette. So now let's draw our cube here. And it should be a bit lower, the shadow. It could still be a bit smaller, like that. Could be lower. And actually it could be wider. So let's draw it starting from -8, and let's have it be 128 plus 16 wide, so that's 144. It could still be a bit wider. Still be a bit wider. There. And now let's still send the cube a bit further back to save the cycles, and now it's running 60 frames per second consistently, so I think we're happy with that. Okay, so now I've shown you a couple of things you can do with a T-line. There's a lot more you can do. This is a very rudimentary texture mapper. There's still I've seen people do environment mapping and cool stuff like that with it. I haven't gotten that far into it myself, but I'm gonna keep looking into what you can do with that. Okay, I think I'm now done for the evening. So, does anyone have any ideas what I could be doing next time? P.S. awesome that we are watching, but yeah, if someone has any ideas what to do, what I should do next, well, you can reach me on Mastodon, on IRC, on Twitch, you can on basically all the demo scene channels. So I'm thinking Shadow could be half transparent, maybe with Scanline. Oh yeah. That's definitely a good idea, and there's also, you know what, one thing I might do next time is show some advanced things you can do with really juggling about the sprite map and using memcopy and SSPR. That's one thing I might do next time, but if you have any other ideas, well, basically, you send me your ideas, and thank you all for watching, thank you all for tuning in, and see you all next week.